Hello, everybody. If you are into science, this stuff is for you. I have a new scientific, well, some people would not call it scientific, but I have a new atomic model which explains a lot of things, I think. And I'm going to be using this medium to explain to you guys exactly what I'm seeing here with this new model. Now, I've written a book. It's called The Galaxy Model for the Atom by John Sefton, and it's available on Amazon. And in this kind of short book, I explain how I came to my ideas about modeling atoms after galaxies and how the observations that we're seeing around us are showing that this is a correct way to understand atoms and galaxies. And in my last video yesterday, I talked about how we can tap gravity, and that's one of the things that comes out of this atomic model, is that there are smaller structures that are radiating smaller spectra of radiation. And the electron is actually radiating a pushing force, a pushing radiation, which is a smaller neutrino. It's the same thing that stars are radiating, which we call neutrinos. But the electron is radiating the next smaller neutrino. And the next smaller neutrinos are right-handed, and they fill all the space, and they feed the proton's right-hand spin. The right-handed neutrino from electrons, the repulsion that we feel from electrons is the lifeblood of atoms. It's what runs atoms. It's what spins protons. It's what spins everything, right up to stars it spins. So there's that. And that's gravity. And we can tap that force by altering the way that the matter absorbs the force. We can change our matter and make it so that it ignores that force from certain directions. And in so doing, we can manipulate gravity. We can tap gravity. But having gravity backwards and thinking that matter just pulls things by itself is what has led to what people are calling black holes. And they say, oh yeah, black holes are proven. They've been seen at the center of galaxies. There's something there. There's an accretion disk. And yes, there is something there at the centers of galaxies. At the centers of galaxies, there is something called a bar. And most spirals are seen to have this bar at their center. Okay, so this bar, they talk about this bar. The Royal Astronomical Society put out this little thing here. Galactic bar paradox resolved in cosmic dance. Okay, so most spirals have this bar, and they've been looking at all these bars. All right, so the bar and in the center and the spiral arms are thought to rotate at different speeds. Okay, that's an observation. If they are disconnected, the bar shows its true and smaller structure. But every time they meet, the bar appears longer and its rotation slower. Okay? So, this new work offers a potential solution to the so-called galactic bar paradox, whereby different observations produce contradictory estimates of the motion of the central regions of the Milky Way. Now, the central regions of the Milky Way, the galactic center, which they're calling a black hole, but it's a bar. It's our galactic bar. And right now, our galactic bar is pointed right at us, straight at us, which might be having something to do with the cyclical things that are happening with the Earth and the planets right now. But the bar is pointing straight at us, okay, right now. Okay, it goes on to say the majority of spiral galaxies, like our home, the Milky Way, host a large bar-like structure of stars in their center. Knowledge of the true bar size and rotational speed is crucial for understanding how galaxies form and evolve. Okay, as well as how they form similar bars throughout the universe. Similar bars everywhere. All galaxies have these bars. Hey, hey. However, our galaxy's bar size and rotational speed have been strongly contested in the last 5 years. Okay, so this is back from 2012, I think. Let me look. I think this is from 2012. Okay. While studies of the motion of stars near the sun find a bar that is both fast and small, direct observations of the galactic central region agree on one that is significantly slower and larger. Okay, the bar, the central bar. It's not black holes. These are bars at the center of galaxies. Okay. Okay, these guys go on to show that both the bar size and its rotational speed fluctuate rapidly in time, causing the bar to appear up to twice as long and rotate 20% faster at certain times. The bar pulsations result from its regular encounters with the galactic spiral arms, in what can be described as a cosmic dance. As the bar and spiral arm approach each other, their mutual attraction due to gravity makes the bar slow down and the spiral speed up. Once connected, the two structures move as one and the bar appears much longer and slower than it actually is. As the dancers split apart, the bar speeds up while the spiral slows back down. Okay? So this is their solution, is that the bar is somehow being pulled gravitationally and stretched each time it gets closer to a spiral arm, I guess, right? So the galaxy model for the atom models these bars and disk structure. In the galaxy model for the atom, the disk is both rotating and also precessing. Okay, so it's going around two axes. And meanwhile, at the center is the bar. And the bar is rotating backwards compared to the disk. It's precessing the same way as the disk, but it's also rotating around the third axis at a certain speed, which causes it to come into and out of the plane of the disk. So when they're seeing this bar, or these bars, appear to be longer when they get attached to the star arm, it's because they came rotating into the plane of the disk. They're not getting longer. They're coming into the plane of the disk. And as they come into the plane of the disk, they're synchronized with the disk's rotation so that they hit the star arm each time. And then they go back out of the plane of the disk and they appear shorter again. Okay, that's what's going on. And so it's like a rotor stator thing. The bar is hitting the disk in these graduated places according to the way it's synchronized as it comes into and out of the plane of the disk. So the central galactic bar has rotations around 3 axes, and it's inside a disk which has rotation around 2 axes. And that's how it's set up. And the way it's synchronized dictates how many times it's hitting that disk, right? How many star arms are being hit in one cycle. And so if you take that back down to an atom, the protons at the center of the atom are a bar. They're not a sphere, they're a bar. So that's why the center of the atom is so hard to hit. It's like trying to hit the end of an arrow that's spinning. It's not like trying to hit a solid sphere. It's much harder. It's like trying to hit a bar end on. And if you don't get it quite end on, then you just don't hit it. Eh? So that's why the center of the atoms are looking so small, as it's not a sphere, it's this bar. And the bar has rotations around 3 axes. The center, the nucleus of every atom, the proton, the bar. It's rotating around 3 axes simultaneously. But it's inside the disk, and the disk is rotating around 2 axes simultaneously. And so the disk is constraining the bar. But when the bar is separated from the disk and becomes able to rotate around all 3 axes with no constraint from the gyroscopic effects of the disk, then these free nuclei, plasma free nuclei, are rotating around all 3 axes. And gyroscopically, if you take something that's rotating around 3 axes and you push it with a certain force, it will push back exactly the opposite direction with the same amount of force. And so what happens with these free nuclei in plasma is, in a gravitational field, they go the opposite way. So the plasma gets shot away from gravitational fields. And other things move counter to gravitational fields. As soon as you've got some atoms, hydrogen and helium, both only have 1 orbit. They only have 1 pair of electrons around them. So since they only have 1 axis, orbital axis, they can turn with the 3 axis rotation that the nucleus is doing. And so hydrogen and helium also both go upward in a downward gravitational field. Okay. But black holes are very popular to talk about, but they are actually these galactic bars. And the galactic bar recently has been found to be spinning backwards and much faster than what was previously thought, which it has to do. If you're doing a rotor stator thing with the bar and the disk, one of them spinning the opposite way than the other. And in our case, protons have a clockwise spin, and the galactic bar has a counterclockwise spin. All right. So that's what's happening with the galactic bar. But recent observations of galactic bars have shown that they are cylindrical. They're a cylindrical structure of many, many stars. And those stars are pretty much all old red giants, which appear to have a much longer lifespan than our regular stars, somehow, maybe. But anyway, if you're interested in science, galactic bars, like black holes, are passé. Forget black holes. It's the galactic bar at the center of the galaxy. Get this book, The Galaxy Model for the Atom by John Sefton. It's pretty short, but it takes you through kind of the logical progression of seeing these patterns and understanding these patterns of what we're seeing. Okay? And gravity can be tapped. If I can get somebody to help me do it, I can tap gravity cheaply. It's not a big deal. It's not going to take any kind of major CERN-like structures, that's for sure. Gravity is very easily tapped. Once you know how it works, once you know how it pushes matter and how the matter resonates with it in order to be pushed. And if you can make the matter resonate differently, you can influence how it gets pushed and from which direction it gets pushed and how much it gets pushed. And you can tap gravity. Anyway, have a good day, you guys. It's been a blast.